So I want to motivate a little bit specifically for random function in this setting because, like when we have hash function applications, we will want to get the idea about the best security of it. The traditional way is to model the hash function as a random function and then analyze in the random oracle model. But the traditional random oracle model doesn't capture preprocessing attackers, doesn't capture time-space trade-offs, so tells us nothing about the security in terms of the time-space trade-off. So motivated by this, in 2007, UNO, and we revisited later, consider a slightly modification of the traditional random oracle model. It's called the auxiliary input random oracle model. Let's begin with the definition. So we have a random function. The usual way I think about random functions is actually very easy for me to think about the truth table of the random function. So it's a truth table, and all the values in the coordinates that are uniformly and randomly distributed. So it's just a huge random string. And you have oracle access to it. Oracle access, I mean, you can specify, okay, I want to look at the fifth location and get what's the value at. So in order to incorporate preprocessing, so we think about the algorithm has two stages. So in the first stage, you can think about the offline stage, before everything happens. You can look at the whole truth table of the random function, then you produce some advice or store some information, like S stands for the space you're using, allow. And then in the online phase, you can make T-queries. So that's the model we're looking at. You take the advice, you make T-queries to the random function, then you do the analysis again. So this is the new model. We kind of think the model is very meaningful and help us to get an idea about the non-uniform security of hash function applications. Regardless of the motivation, I think it's just a clean model to study time-space trade-off. Any question about the model so far? If not, we're going to do some homework about the model, okay? So let me, in order for you to get more idea about this model, have idea about how to attack things here, I would like to share with you my favorite problem. So it's a very easy problem. You are given a random function from n bits, from n to 0, 1. So if you think of the truth table of the function is a huge random string of length n, and you give it as oracle. And your task is I give you a random x. You tell me, you predict what's the value of OX. Of course, you cannot cheat. You cannot query OX. Okay. And your goal is to maximize your advantage. It's how much better you do than random guessing. So recall we have two important parameters, S and T. S is the length of the advice, and T is an oracle query you can make 2O. Okay, let's try to prove some lower bounds. Okay, so lower bound on the advantage. Okay, let's begin with some special case. What happens when S equal to 0 and T equal to n minus 1? Means you cannot have any advice, but you can query everything else except X. What's your advantage? Yeah, perfect, 0. That makes sense. Essentially, the only thing you can do is you can guess it, and have no advantage. What happens when you have 1-bit leakage? Yeah, essentially, yeah, you should consider 1 minus 1/2, so it's 1/2. Essentially, you can now answer every position. And what is the leakage you're using? Yeah, so the leakage will be the parity of the everything. So you ask everything else, and you get what's the value of yourself, your XOR. Does that make sense? Okay, now a slightly more challenging one. S equal to T equal to square root n. What's your advantage now?
Same.
The same. Any other answers? Again? A matrix. Yeah. So the answer will be the same. Essentially, you partition into chunks. For every square root n chunks, you store the XOR of that. So starting from now, there's nothing there's no difference between we study is a random function or arbitrary function. This applies to any function. So there's some advantage of studying random function, give us some easy attacks. So this is one of the case. What about S equal to 1 and T equal to 0? What advantage you can get? So you can store 1 bit, but you can make no oracle query to O. What will you store? Yeah, so you just store the most likely bits, right? So it's the majority. And storing the majority give you like already like non-trivial, much better than 1 over n, so give you 1 over square root capital N advantage. Like this, or like very easy to see for random function, but maybe for like arbitrary function, you take more efforts to design the attacks. Okay, more bits of.
Yeah, what did you say before about 1, 2, 3 apply also to arbitrary functions?
Yeah, like you don't need O to be a random function. It's like.
No, but if it's a constant function, I have advantage half in case 1 is 1.
A worst case
Yeah, okay. Well, if you put a 0, I will give you full mark, so it's okay. Like now you have more leakage, like what do you do? But still not curious. Yeah, so the answer is the S is going inside it, so the square root S over N. And the idea is like now you part it into chunks, like S chunks, and for each chunk you store the majority. So, okay, now is the very hard bonus problem. What is the answer for general S and T? You just need to guess, and you get 100 marks. I only have half hour, like you just do random guess. Yeah?
Don't you carry the solutions in 5 on S? If you take S to the n.
Yeah, then it's meaningless. I agree. Yeah. So let's say S is S up to n.
Minus 1 also doesn't work, right? So what?
It's almost there. Yeah. There's some constant there. I'm not like talking about.
Some constant that is greater than 1. Is that what you're saying?
No, like there's some constant in the lower bound I ignored. So yeah. So if they're in the same order, I think yeah. I'm just talking about.
You're not getting extra time.
Okay.
You're not getting extra time.
Well, so the answer is like T is inside. So you can come up with an attack and like essentially using majority combos with parity, and you can get this advantage.
So it's tight.
So is it tight? Can you upper bound epsilon? Well, I want to emphasize, like, although we're upper bounding like epsilon, it gives lower bound for time space trade-off. So we studied this is for like lower bound in time space trade-off. Is it obvious? Okay. So once you give upper bound on epsilon, you get a lower bound on like trade-off between ST. Okay. Okay. Now let's try to prove the upper bound on like the advantage on epsilon. Like, how to prove it? Yeah. You miss.
Yeah, can you explain it maybe just case 1? What is S equals 0, T equals n minus 1? What is the 0 means?
The advantage of the best attack.
0 means that you're just getting, like, if you're allowing n minus 1 order queries.
Yeah, but no leakage. Like you know nothing about the random function.
So why is this a 0 advantage? Can't you, like, somehow with some probability or?
Yeah. Like we consider the epsilon is minus half. Like how much better you do than guessing.
No,
you can ask everybody else, but you cannot ask X.
So it's not a question of holding value, it's a question about.
About predicting, yeah.
Yeah.
The output is just a single bit.
No.
Yeah. So I guess then you miss what's happening here, but anyway, it's just the parity and majority, and you choose one and then works. Okay. So this is my favorite problem. How about your favorite problem? Like any construction around Oracle? How security is now against preprocessing algorithms? And is there any way you can make it as secure as before, like easily? So one remark about now working in this new model is like most techniques we have in random Oracle model might not apply. And the reason is like many techniques in random Oracle heavily rely on the independence and the uniformity of the value of in the truth table, but a little bit leakage already ruin the dependency. So you need a, yeah.
So, why do you think it's a new model? It's not just the timing and trade-off started by Herman. I mean, what's the difference between the question you're asking and the question asked before?
Maybe one difference is we specifically care about random function. Does it make sense? We specifically care about just random function.
And not random permutation.
Permutation we'll talk about later, but in this model only random functions.
Also, anyone cared about that. Yes,
It's upper bound. Like now we are like more aiming in like a lower bound.
The model did appear before, right?
Yeah, it did appear before. Yeah, but maybe they want to emphasize like the non-uniformity and the random oracle setting. Like it's just recently revisited now. But like if you want to use it to study time-space trade-off, like already appeared before. Yeah. Okay. So let's see what toolbox we have in the random oracle, the new model, and not new model like the auxiliary input random oracle model. Like Luca already talked about like compression argument. You have seen how it looks like, and we will see it again in the afternoon. But today we're going to talk about another approach. The reason I put optimal there is like often the case if I use compression argument careful enough, I can obtain almost tight like time-space trade-off. This is in contrast to another proof techniques I'm going to mention later. Is also the emphasis of the talk. It's called pre-sampling. I'm going to describe later. But the high-level fitting of this model of this technique is like it's very easy to use. I will show you like why. But there's one like unsatisfying thing about the pre-sampling technique back introduced from Uno is like it doesn't give you like tight bounds. So the main message of our work is we introduce some new tools. Essentially, we improve the pre-sampling to the almost to the optimal case, and now you have easy to use tools. And we suggest you to look into these tools. It's very easy to use, and then based on that, we can actually give some simple combiners, like take a construction and combine to another construction can help you to defeat preprocessing. So the rest of talk is we're going to describe in details. Like I will introduce what a tool looks like and how to use it, and if I have time, I show you the combiners and the proof of the tool. So like you're ready? Okay. Okay. The tool. So before I describing the tool, let's think about an easy case for us to prove in like a lower bound security. So what about the leakage or the pre-sampled advice? It's very simple, stupid, like just leak several locations from the random oracle. So you choose, let's say, S coordinates from the truth table, then you just store the value and pass to the online phase. Yeah. So now you think about from the perspective from the online adversary. When you look at the advice from the pre-compute stage, now you look at the random oracle. So it will look like this to you. So some locations are black, and some locations are white. So here black, I mean the values are fixed. Actually, you know what it is. And the white are still pretty clean and it's independent and random to you. So that's how the random oracle looks like to you now. So if you look at the truth table, if you look at this case, so it's pretty much look like the original random oracle function except the black thing. So if you ignore or think some way to deal with the black thing, you can apply standard random oracle techniques because you have independence among a lot of entries. So it should be an easy case, right? In particular, if we want to analyze one-way function and pseudo-random generator respect to this function, and if you think about that, the extra thing we need to pay is when we pick a random preimage, and when the preimage fall into the black thing. And the black thing is only have S of them, so you get S over N. And the T over N is the standard random oracle security. So then you get it's very easy to prove bounds for this stupid leakage. Does this make sense? Okay, so now come to the tool. So essentially the pre-sampling says you can reduce the general leakage to this variant of this very easy case. What do I mean? So we consider intermediate oracle called P bit fixing random oracle. So what does it mean? So So the P locations are fixed by the adversary in the pre-computer age, like pre-computer stage, and all other locations are resampled uniformly randomly. So you can choose the P location depending on what function you get, but later on all the other locations are like resampled, like they are independent uniform like entries. So this is the P bit fixing around the oracle. And the high-level idea of pre-sampling just says the best advantage you can get in the auxiliary input around the oracle model can be upper bound by the advantage you get in the P bit fixing model plus some extra thing.
I didn't understand P-bit fixing versus what you had in the easy example in the last page.
Sure, the easy, so the easy is very easy. It's like only like fixed S locations. In the P-bit fixing model, the location I leaking could depend on the host truth table. Then I resample all the other locations.
What do you mean the locations you leak might depend on the truth table?
For example, I first look at the whole truth table and compute the sum. I say, okay, this is 5. I leak the 5th location.
Oh, it's fixed location that the preprocessor can first look at
Yeah.
everything and do something smart.
Yeah,
But
yeah.
then just the locations can be like general leakage. I mean, I can just forget about the fixing, right? I need to also tell you which locations I'm fixing. So there I can like hide all my, like put all my leakages there, right?
Right. You tell the locations also the values.
So I can put general leakage just in the locations, right? I mean, I'm looking and doing like arbitrary preprocessing, and then I'm like, this is the information that I actually want to tell you. So I'm not going to, I mean, I cannot tell you this information because I'm only allowed the bit fixing. So I'm going to sort of.
You can do that. You can do.
As a sequence of locations and say, well, these are the locations, these are the values.
You can do that. You can fix the value in an arbitrary way in those locations. You can put what. But the other location, they're resampled, so they have no correlation between.
But it's more leakage than what you leak just from the fixing. I mean, the fixing will leak to P bit, and you get P times log n just from the location.
So in this talk, we don't care about log n. So.
But it does leak actually, because the location is looking at, so it does split.
Yeah, but she resamples all the others. After she does that, she resamples all the white cells.
No, but then it doesn't. Yeah, no, this doesn't.
So the tagger just fixes P locations arbitrarily, the rest is, forget about the selectivity, the rest is resample, so it doesn't matter.
Okay, so. Okay.
Yeah, is it clear? Like it's very important. All the other locations are resampled. Like now the values.
It can depend on the specific values that are in these P locations, not in the other locations. Okay.
It doesn't really matter, just P locations are fixed, we don't need the subtlety, this adaptive thing, just fix P locations so they're random order, the rest is random. That's the model.
But then what's the difference from this is really
So the fact that you choose the location based on looking at all the table is major.
It's possible maybe you can gain more things, but I'm not.
It's not possible. Like when you sample the other locations, then what you saw there will not affect anything, right?
Yeah. Okay. So just for simplicity, let's just think about it. P location fixed, like, and the other things are uniform.
But then what's the difference from the previous model?
How would you leak the value of majority? You need to fix it. Say leak the value of the majority.
No, okay, I don't understand.
So let's think like the previous model and this one are the same. Okay, I will like explain the.
They're the same? She's saying
For simplicity.
assume they're the same.
Yeah.
I know there's some subtlety, but let's ignore it. That's what she's saying.
But the definition of this model is just okay. You fix P locations, and then other locations are like sample uniform randomly. For all the primitive we care about, like proving one-way function in PRG, like there won't be any issue like he. But anyway, so let me continue. Okay, so now the question is what cost you pay. Is the function depend on the number of locations you prefixed and S and T. So when Uno introduced the idea of pre-sampling, he showed like the upper bound should be square root of ST over P. And so in joint work with Evgenia and Jonathan Katz, we show like this epsilon is at least ST over P, so there's a square root gap there. And in this work, we figure out, okay, so ST over P is the right thing. It's like, can you
So this is the difference in the best advantage you can get in one model versus the other.
Yeah. So for example, let's apply, if you like assume this, accept this for now. Like, if you want to prove the security for PRG, have we like mentioned before, like in the P bit fixing random oracle model, like P location fix and all other uniform random. In this model, if you want to do the security for PRG, the extra term is just the fraction of the number of bad locations. It's like roughly P over N. It's just the probability the image fall into the bad locations. For if you fall into a good, like clean location, then the standard random oracle technique gave you like T over N. I omit T over N here, just for simplicity.
Just to make sure I understand.
Sure. Sure.
So it's the same game that you do before. You're going live, you give it advice, so that you prove you're guessing that. On the left-hand side, you allow arbitrary advice. On the right-hand side, you are restricted to bit fixing. And you said that there's a trade-off. There's trade-off between giving this advice to other advice for your advantage of using it for guessing the bit method, right?
Yeah.
Yeah?
But you can gain at most STO.
Most of that.
Yeah.
I also just want to make sure.
Sure.
So you're saying if I'm willing to pay ST over P price, I don't need to think about complicated smart leakage. I can think about stupid leakage, and it's really not.
That's it. Yeah.
Okay.
Yeah, that's the message I want to say. Like, if you pay the membership fee, you just get into the case. Okay, so for PPT fixing, like it's very easy to analyze like P over N roughly, and then you pay the cost ST over P. Then you choose the best P, like minimize the advantage. So then you get like you choose some P, and then you get this bound, and it's almost optimal. Like it matches all the best bound we know, like we prove for PRG. So this is the proof.
This is Wunu or this is the
After Wunu. Wunu, they will get like 1 over 3 here because there's a square here, 1 over 3. Yeah. Okay. So now the question we continue. We want to prove bounds for one-way function. So for one-way function, actually for bit fixing random oracle model, security is the same. It's P over N. So if we apply this again, we will end up with the same security as PRG. But actually for one-way function, we should expect like a better bound. So we're hoping to prove like better bounds for one-way function. Like any way we can do it, like given the cost is already optimal. So this is the second nice trick I want to convey to you. So look, I have a question. Yeah.
If you're looking at, say, inverting a constant fraction of the inputs, you're already getting the...
Yeah, if you're happy with constant fraction, you already get a trade-off. But we want to look at what's the dependency on epsilon. Okay, so there's another very complicated problem. Question here. So suppose you have two distributions. Both of them are like over bits, n bits string. One is uniform string. Like each bit is half, with like each bit is 1 with probability half, and another is slightly biased. Say like the bias is 1 over n. Now is the question. If you can prove something is negligible under the first distribution, can you prove something is negligible for the second distribution? Well, so the first thing come to your mind is maybe you want to try to bound the statistical distance between these two distributions. But the statistical distance between these two distributions are like noticeable far. If you just look at the first coordinate, the bias is already noticeable far. And do you want to answer yes or no? Or how many minutes do I have?
7.
7, okay.
Yeah.
Yes, no, yes, no.
Second, A is arbitrary event.
A is arbitrary event.
But it's small, right? Therefore it holds. But I mean, Pinske's lemma is better in the corners than in the middle.
Uh-huh. So your answer is yes?
That's
Yes,
for concentration.
Yes,
Yes, that's for concentration.
Okay. Well, so there is a simple way to say is if you look at like the property mass point-wise between this distribution, you can bound the multiplicative error. So it's actually just an upper bound. It's a constant upper bound. So you can actually bound the ratio between these two probabilities and the constant, and that's good enough for you to show this is negligible. You don't need to bound yourself to like additive cost. If you consider multiplicative cost, you can afford much larger like polynomial number. So this is the message I want to convey. It's like for one-way functions, like bounding the multiplicative error is good enough. So let's come look at what's the multiplicative version of pre-sampling can get. So we figure out like actually you can get a multiplicative version of pre-sampling. So the multiplicative cost is 2 to the st over p. And if you set p to be st, so the multiplicative cost is just constant 2, so you don't care. And so that's you're already done with the proof because we know for if you prefix st locations and the security is st over n, like if you just so that's how you get the security bound for one-way function in this model. Yeah, I think there's a very nice conservation message here. It's like for those kind of applications like one-way function, we don't care about the multiplicative error. The AI ROM model is just the same as ST bit fixing model. It's like essentially just ST location fixed. So you can prove things like very easily. So for example, like one example I want to show is like, so we have been talking about how to defeat preprocessing. And one standard way we use is sorting. Yeah, 5 minutes, yeah, we'll be done with it. So what is sorting? Like in practice, like when you use the random oracle, you're not using the whole, wherever you want to do something, you append a random public sort. For example, if you want to hash a password, you're not hashing it directly. You append a random public sort and you hash together with the prefix. And in theory, this like means you're using a family function instead of like a single function. If you think about in terms of truth table, you just say, now you view the random oracle, the truth table is a matrix. You're choosing a random row from the matrix, then use it as our function. And why this defeats preprocessing? What we claim is like if you have something which is secure in the random oracle model with epsilon advantage, now if you're using sorting, use a huge matrix and pick a random row out of it, the security will be like you sacrifice a little bit the security, like st over k, for applications like one-way function. Okay. The reason is that if you apply the pre-sampling lemma, so this is equivalent to the clean matrix, except st locations are bad. And the probability you're hitting this bad row is just st over the k. So there's st rows are bad, and at most st, so you pick a random row, the probability hitting the bad row is like st over k. So that's why sorting defeats preprocessing. So there's another sorting scheme. I'm not going into details. I'll just show you the construction. So this sorting will pick a random row out of the matrix. In order to get almost the same security, we need to set the matrix has size roughly n squared, like say k.
But previous example also preprocessing L, right? And also showing that preprocessing is not L, also compression argument.
Again?
You don't require this pre-sampling to show that sorting defeats preprocessing. You could do it because it's also using compression.
Yeah, you can also use compression, but then for each security game, you need to do it again. So I just mentioned the construction. Like this sorting is picking a random row from the matrix, but they have the disadvantage. You need the matrix to be huge, the domain to be huge. And there's one way to improve this. It's like the new function we get is like still we view as a matrix. We shift each row randomly, then XOR them. And this can help us to improve the domain from n squared to n log n. So this is another way to do sorting. And if you want to do more randomness efficient, you can pick the random shifting for each row like pseudo-randomly using like random walks on expanded graph instead of picking them randomly. Okay, so this is another way to sorting. So here is just a high-level idea about the proof. No proof? Okay, so let's go. You can read the proof in it. I have a summary. So what I talk in this talk, so we want to study time-space trade-off for problems based on random functions. And the auxiliary input random oracle model, although it's a slight extension of a random oracle model, is pretty nice to study in this context. Can help us to get some conjecture non-uniform security about hash function applications, can help us to study time-space trade-offs. So the main message from the talk is pre-sampling is a very nice tool, help us to reduce the complicated leakage to easier leakage. And we have two versions of that, you can either pay additive cost or multiplicative cost, and this gives you almost tight bound for 2 examples of that. For sorting, we can prove generically defeats preprocessing either by prepend the public sort, or there's some other way to do it. So I want to mention, besides random functions, we can also do random permutations or other random likely structured sorts, like ideal cipher model, general group model. So you can also, in the drawing work with Sandro and Evgeny, we extend the pre-sampling techniques to other idealized model. So you can also use these two in other idealized model to prove non-uniform bounds. Okay, so open problems. So the first open problem I mentioned is that pre-sampling is quite cool in terms of it's applied to many applications, help you to get it bounds. But if you want to prove better bounds, there's still room to help you to prove better bounds for specific primitives, including one-way function and PRG. For one-way permutation, the time-space trade-off is already tight, but for one-way functions, there's a gap there. And the next talk we'll talk more about this. And for PRG, there's a question of, is the T really necessary here? For the predicting game I showed you in the beginning of the talk, the T is there, it's tight. But for PRG, we're not sure if T is necessary. So the second open problem is... Okay, so just want to mention, can you come up with pre-sampling for quantum round oracle? This would be cool, yeah.